the most important thing, we need to ask ourselves, what are the properties of this electron we want to think about? And remember, when we make a choice about our system, we want to measure something particular, and we're going to have a set of wave functions that are defined with that property, right? When we wanted to measure color for our electron, we defined an electron in the color basis, which means it's a mix of white and black, right? So we need to find what's a useful variable that we can look at for our electron that we can define our wave functions on, right? What are some states that give us physical observables for the thing we want to measure, right? And in physics in general, the things that we want to measure are things that are conserved, things that have conservation laws, right? So momentum is conserved, right? You have two particles colliding at two momenta. The momenta of the result is still the same as the original, right? Momentum just gets transferred between particles. So momentum's useful. Position, right? Space is conserved, right? Physics in this spot is exactly the same as the physics in this spot, right? If I move the box in space, the physics doesn't change. So position is conserved. Right, so let me just write that down really quickly. Right, so our conserved quantities is space, or x, right? Position, right? Physics is the same in all positions in the universe. It doesn't matter if I do it here in Buckman or I do it in Dodds. Physics are the same. Momentum is conserved. And of course, because as we'll see in just a second, I'll rewrite it, energy is dependent on momentum and position, energy is also conserved. Right? So these are things that are always conserved in our system, and so they're very useful things to track, right? They're things that don't like magically disappear, right? That we lose energy to something that is unobservable, right? It's always conserved. At least we assume so in our system. So it's useful to measure these three things, right? And this is all physics. This is literally all Newtonian. This is just the physics you learn in general physics. You learn things about the velocity or the momentum of a particle. You know about its position. You know about its energy. And we study the motion of things, the behavior of stuff using these three quantities. That's all you need to know. So we'll stick to that, right? There's nothing new. The physics, the kind of thought that we have about the way the universe works doesn't really change. A different perspective on how it works in the microscopic world, but the same things are still conserved, X, P, and E, conservation laws. So let's come up with something that we can define our wave function for our electron in terms of these conserved quantities, and energy is a natural choice, right? A very natural choice, because we'll go back to the first couple lectures when we talked about the kinds of experiments people were doing. They realized they needed this new theory. Remember, atoms had these stick spectra. Right? They didn't have a continuous absorption spectrum like a big broad hump. They had these little lines in their absorptions. Right? And that indicates that these energy states are discrete. They're quantized. Right? That atoms or electrons or systems, they can't exist at any energy. They can only exist at specific energies. So we can think of that, well, what if we think about our wave function in terms of states of the electron that have fixed energies. Right? We want our electron to have different energies. They're fixed, they're quantized, so let's do that. So our operator is going to be the energy operator, right, which is the Hamiltonian, which is the sum of the kinetic and the potential operators. Right? That's the two types of energy we have, motion and potential. And we said that, again, the potential function for this box is very trivial. It's 0 inside and infinite outside the box. Right? The box, basically, when the electron's in the box, it acts like it's free. It's just a vacuum. There's nothing there. It just acts like there's nothing there. And then when it hits the walls, or if the electron is on the wall, the potential is infinite. So the electron can only exist inside of the walls, right? Okay? And so when we're thinking about the energy inside box, right? The electron can't be outside of the box, right? It's impossible. There's infinite energy there. That we can basically get rid of the potential. The potential is 0. All right, so we're just left with a kinetic energy operator. And we showed that the kinetic energy operator is the momentum squared over 2m. That's just 1/2 mv squared, but you're replacing mv with momentum. And this is equal to h minus h bar squared over 2 times the mass of the particle times the second derivative of the wave function. Okay. So our equation, our Schrodinger equation, right now we have the Schrodinger equation, which when I get lazy, I'm just going to write Schrod, which says that h psi is equal to e psi. Oops, sorry, I forgot the psi here. So our wave functions satisfy this equation, which is that when we operate them with the Hamiltonian, we get the wave function back times a constant, the energy, right? And this is just basically saying that the second derivative of the wave function with respect to position is equal to the wave function times a constant. Right, we have some numbers on the outside here, h bar squared over 2m and e. Right, that's the energy. This is Planck's constants and pi's. This is the mass. They're just numbers. So if we just get rid of all the numbers, we just ignore them for a second, we see that the wave function satisfies the property that the second derivative of the function gives you back the original function. And we worked out we spent a good amount of time thinking about this problem, applying the boundary conditions of our walls and so on and so forth, right? And we came up with a really nice solution set, right? We came up that the wave functions, which are indexed by this integer n, are 2 over L sine n pi x over L, and that these satisfy an energy equation, h squared n squared over 8ml squared. Right? This is our solution, right? And this is, all we did was just a little bit of math, just a little bit of calculus. And we made sure that our function, this wave function that we chose, the sine function, satisfies all the properties of the boundaries, right? That it goes to 0 on the edges, that it integrates to 1, everything that we need to know about our wave function, and it all works. And just from that math, right, just from the boundary conditions, we magically came out with that the energies are quantized by this n, where n is 1, 2, blah, blah, blah. Right? It can be any integer above 1. Stop doing that. Stop doing that. Stop doing that. Okay. I think my wrist is touching it. There we go. So it can be any integer greater than 1. All right, this is kind of where we left off last class. All right, so remember that wave function specifies the system completely. All right, so the electron is represented by a sine function, right? It just is a wave that has different characteristic frequencies, right? The frequencies of the wave are n pi over L. And so every time n increases, the frequency increases by an integer number. Right? So we go from a unit frequency of pi over L to one that's 2 pi over L to 3 pi over L. These are kind of like harmonic notes, if you will, right? You have an A note. There's the next octave. That would be 2 times the frequency. The next octave after that would be 3 times the frequency of the second harmonic. And the same idea here, right? We have these harmonic waves. They're not really harmonic because the energy is proportional to n squared. So even though the frequency increases by, say, 1, then 2, then 3, then 4, the energies increase by 1, then 4, then 9, then 16. Right? So they're not equally spaced, but in terms of their wave properties, they have harmonics, just like a normal, like a pluck, like a string. Right? You can imagine, some ways this electron is acting like a guitar string that's tied between 2 boundaries. The wave can't escape those 2 boundaries, right? The end of your guitar and then whatever the thing at the top is. I'm not a musician, so I don't know what they're called. But right, you can think of that being the length of your string. And of course, depending on the length of the string, you have a fundamental note associated with that, right? Which is a wave or a sound whose frequency is one, whose period is one whole length of the string, right? And then you'll have the next harmonic, the next octave, which is 2 periods on the length of the string, then 3 periods, then 4 periods, right? And so electrons work exactly the same way, right? You can think of the box as your string, the electron is the string itself, and it has these fundamental oscillations, these conserved oscillations, which are the harmonics of the string, which are dependent only on the length, and also the mass of the particle. Of course, now, unlike waves, which don't have a mass, right? Sound waves don't have a mass. Here we have something that's also massive. Right? This is that wave-particle duality that I'm talking about here, is that we have something that acts like a wave in space, but has energy like a particle. This distinction between energy, wave, and particle, right? The fact that there's a mass, that the energies are defined by a mass, but the properties in space are like a wave. Right? You can see it right here. Right? This is a really beautiful, elegant result, because all of this quantum mechanics ideas, quantization, and these wave functions, it all falls out of the math very quickly, very easily. And it's almost a wonder it took people hundreds of years to figure this out. But again, this is a response to experiment. No one would have ever thought to think of these things until they start to see that electrons start in small boxes act like waves. So no one would have ever thought that this would be true, even though the math is very simple. And in fact, Newton had the rules to figure this out. Newton or Maxwell could have figured this out no problem, but they have nowhere to look, right? They didn't know where to look to begin with. So even though this math seems very simple, it's the intellectual jump we have to do to just realize that this actually happens in microscopic scale is the hard part. It's the experimental part that took so long. Okay, so I want to explore this system today. All right, I want to look at what these wave functions look like. And then what I want to do is I want to start, right, we have an electron, we want to start measuring things about it, right? We want to measure its properties. All right, so we're going to look at that today. So, I'm going to switch slides here. Again, it's very easy, right? I can just make a box and pick an n, and I can look at what the wave function looks like for that n. So let's do that. So what I have here is some code I wrote that does exactly that. It calculates the wave functions for my particle in the box and plots them. And I'm going to plot the first 5, n equals 1 to n equals 5. And so let me show you what this plot is here. We'll start at the bottom and then work our way up. So on the left here, I have the wave function itself. Okay? All right, so this is n equals 1, n equals 2, 3, and 4 on the screen. Right, so we're going up. The x-axis is the box. The box is, I've rescaled the box, so the box is where the center of the box is at x equals 0. So this box is extending from minus L over 2 to plus L over 2, so I've just shifted it a little bit. That just makes my math a little easier, because I'm integrating from positive to negative at the same boundary. It makes the math just a bit easier. And you can see that, right? So our fundamental note is, let's go over here, is 1/2 period of a wave. Right? It's got this very, very broad, right? It's just basically half a sine wave, right? And if we go to n equals 1, 2, the wave function now completes an entire period, right? It's double the frequency. Now we have a single frequency, now we have double the frequency, half period, whole period. This is 2 periods, right? So we got, so it's 1.5 periods, sorry. Right, we have one whole period here, and then another half period, and we can keep going, right? And you can see that every time you go up an n, your electron completes an additional pi of phase across the box, right? This is, again, just thinking higher frequency notes, right? The higher frequency waves, they're octaves of each other. But as you can see, the energies are spaced differently, right? The spacing between, these are all labeled at energy. So here on the x-axis of energy and units of 10 to the 5 inverse of 10 to the 5 wave numbers. We won't worry about the energy scale at the moment. But the y-axis is energy here, and you can see this spacing is not quite getting to the next one. So they're not equally spaced levels. So the energies aren't harmonic. that the energies are spaced equal and linear, but the frequencies of the waves are. Okay? And that's the unique property of these square boxes, is that you get a energy spectrum that goes as n squared, but your wave functions are harmonic. They increases, their frequency increases as a function of n, not n squared. Over here on the right, what I've done is I've squared the function. Right? So this is your probability density distribution. Right? This is psi squared on the right. Right? Remember what psi squared tells us. It tells us, right, if I pick a point on my curve on the x-axis, anywhere, the height of this psi squared tells me the probability I'll find the electron there. Right? So this tells me exactly, if I made 1,000,000 measurements of where my electron is in the box at random, I'm going to get this distribution. This is what the histogram will look like. And so what does this tell us? Well, we can immediately do statistics on this, right? What's the average position of the electron in the box at n equals 1? Well, it's right in the middle, right? The highest probability zone of the electron's position is right in the middle, right here at x equals 0, right? And where the probability peaks. So on average, right, we're going to take statistics. And it turns out the only thing we can do in quantum mechanics is take statistics. Right? Because this is what we observe in the lab. Right? How do I measure the position of the electron? I ask the electron, where are you, 100 times, and I make a distribution of that result, and you get this by the central limit theorem. This is what you get for infinite measurements. And it says that on average, the electron is in the middle of the box. But as you can see, it's delocalized across the entire box because it can literally be anywhere. The probability only goes to 0 at the edges. So there's a non-zero probability of the electron being anywhere in the box with a peak, a mean, right in the middle. Okay, so on average, we'll find it in the middle, but there's no reason for it to be, so reasonable chance for it to be anywhere. All right, this is what I mean by delocalization. Remember, energy is related to momentum. So what I've done is I've fixed p squared, if you will, momentum squared. And when I know something about momentum, I lose information about space. And we'll formalize that hopefully next week. This is what's called the Heisenberg uncertainty principle. If you know something about position, you lose that in energy or momentum. And so if we have a fixed energy, we have a delocalized space variable. So the electron can be anywhere, right? It has wave-like properties. A wave can propagate and exist anywhere in the space that it exists. So it sits right there. So now the question, of course, is, well, let's keep taking averages as we go up and in, right? Does the behavior of the electron in terms of position change as a function of energy? And so let's take the average of this function for n equals 2. Notice that if I draw a line from x equals 0, right, this is the most probable place for it to be in a ground state, there's no probability of finding the electron in that spot at n equals 1, right? The function goes to 0 here. So the electron, the place where we're going to find the electron in n equals 2 is here, most likely, right? Or here. It's a bimodal distribution. So you have effectively two modes, right, here and here. But they're equally spaced, right? This potential, or the wave functions, are symmetric about the middle of the box. Right? It goes the same way and this way. So here we have an average, basically two modes for our position distribution here and here. And the average is going to be the average of those two modes, because it's symmetric. And so the average is still in the middle of the box. But that's just because it has an equal probability of being on the right side of the box as it does the left side of the box. So even though this is the average position, we actually never measure it at the average position. We just measure it at the two means on the edges, and those average out to the middle. Right? So there's some really important spatial information that we lose when we average. Right? This tells us, again, if we just took a naive average, we'd get in the middle, but we'd never find the particle in the middle. We'd always find it on the edges, on these two peaks here, which of course average out to the middle, because it doesn't matter whether it goes left or right. It's symmetric. So it's complicated, but the interesting thing is that in this box, as a function of n, there increases the number of places where you can't find the electron. Right? So here within the box, you can find the electron anywhere, but here there's a specific place, one specific place in the box you can't find it. Here there are two, here there are three, and so on. In fact, these continue up, right? So for n equals 2, we have one dip. N equals 3, we have 2 dips. N equals 4, we have 3 dips. Right? And so they tend to scale as n equals n minus 1. And these are called nodes. I don't know how to write on this, but these places where the probability density goes to 0 are called nodes. And nodes are very important structural information because, again, this tells you something about what I call the structure of the electron in the box, right? The structure of the electron in the box is where do we find it, right? How does the electron distribute itself into space? And there's this node in the middle, which is where the electron can't exist. We're going to see nodes everywhere, right? The orbitals of hydrogen have nodes. There are places around the hydrogen atom that certain electrons can't exist in. And what you might notice is that as energy increases, the number of nodes increases. Or you can think of the more distributed the electron is, the more delocalized it is, or the less information we know about where it is, the lower the energy. You can think of it either way. Right? They're correlated, though. And when we get to molecules, that'll be very important. When we count nodes, it'll tell us something about the energies of these levels. So we'll look at that again. But this is this is unique to quantum mechanics, that our particles have positions in the box where they'll never be. And this is just due to its wave properties. Okay, so what I want to do, so here's another thing. So it's not hard to show that if I go up to the next level or the next level or just keep going, the average is always in the middle of the box. All right, that's because all of these functions are symmetric about the center of the box, or the same on both sides of the box. Cut it in half. So the average position you find the electron in all states is in the middle. But there's another number that we care about. There's many numbers in statistics we care about, but there's one in particular we really care about, which is the standard deviation, right? The width of your uncertainty. So I can, if we do this in lab, or imagine we're doing this experiment in lab where we're measuring psi squared for an electron in a box. I ask you for the average, and you're going to tell me it's always in the middle of the box regardless of the energy, on average. But I'm also going to ask you, what's the uncertainty? Right? And so you have to calculate a standard deviation, right, which says something about the width of this probability distribution, how wide it is, and how many possible values there are within a standard deviation. And as you can tell, the standard deviation changes as a function of n. Right? In fact, if you can think about it, right, so the standard deviation here is minimal because the mean's right in the middle, and it kind of smoothly rolls off. And of course, my laser pointer dies immediately. Right, the standard deviation here is like this. Right? Somewhere in between here, right? It's like that wide. But now when we go to n equals 2, the standard deviations increase because most of our molecules, or our electrons, are on the edges here. Right? And they become further and further away. Right? So the standard deviation of our measurement increases as a function of n. So what does that mean? Well, it means that, again, the average is the same regardless of energy, but the breadth at which the electron can exist extends. So it becomes even more delocalized in the box as energy increases. And basically all that means is what's happening is it's moving more and more rapidly in the box, and it spends more time on the edges than it does in the center because it's moving rapidly, and you're starting to see that distribution start to spread out. Of course, it's oscillatory, but let's take it to the most logical extreme level. What if we make n equals 1,000 or something like that? So let me just draw that instead of plotting it. It's probably easier just to draw it. So again, let me just redraw n equals 1 here. Again, remember the thing we observe is psi squared. We never observe the wave function. We always observe the probability of it, which is psi squared. N equals 1 again just looks like a half of a sine wave, like this. It actually has some negative curvature, like this. Right? And we saw that the average position of that curve is at L over 2. Right? And so we can say the standard deviation is some width delta x, or sigma x. This is the standard deviation. Of course, you might also call it, and we'll use this term either, another term for it would be delta x, the uncertainty in the value. Right? So here's the interesting thing about this result. So what's the implication of this? Well, what it means is that if we're making a million measurements of our position, right, making a huge data set of the positions, the electron can be at random positions. We make a million of them, we get this distribution from our analysis. And I ask you to report to me the average position and your uncertainty. Right? And you're going to report to me that the average is L over 2. Which is, I'll write this again with averages with these angular brackets. I'll redefine that in a minute. You're going to report this, and you're also going to report your uncertainty. Okay, and you're going to be like, well, I have some uncertainty in my measurement because of experimental error. And I'm always going to have some error because of my measurement. Now imagine you had a perfect measurement instrument. No error, no noise, nothing. You can measure that position precisely. You've gotten rid of all, or maybe you've accounted for all of your experimental error, and you're confident that you can model it. And you go do this experiment again, and you still have an uncertainty to your position. It still has a width. Well, the reason why it still has a width is because that width, that uncertainty to your distribution, is implicit. It's inherent to the wave function. The system itself has some uncertainty to where it is when you measure it. So this standard deviation, this error, the uncertainty in your measurement, uncertainty certainty is intrinsic to the electron. Right? No matter how perfect your instrument is, your precision on the average of the position of the electron is never better than sigma x. Right? And that's dependent on the width of your wave function, how broad your wave function is. Right? So you can never do better than this. When we look at bonds, for instance, we're going to have a similar idea. We're going to have a wave function representing a specific state of a bond, and it's going to tell us what the average length of that bond is in the same way this does here. We're going to measure the position of the bond, the length of the bond. We're going to get an average, but we're also going to get a width. And that width automatically means that there's some implicit, inherent uncertainty to the bond, the length of the bond. The bond length is not perfectly defined. It has a perfectly defined average, but it also has a non-zero and perfectly defined uncertainty too. And no matter what you do, you can't do any better than that. Right? These are the limits of quantum mechanics. When we measure quantum mechanical properties in a classical setting, which is we're taking a wave, some wave-like property, and projecting it onto position space, that naturally leads us to have this natural width to our measurements. And therefore, these things are explicitly and intrinsically uncertain. You can never measure a bond length or the position of an atom electron at fixed energy, at conserved energy. That's the important thing. Right? The assumption here is that the energy is constant. So if we have a constant energy system, you can't know the position of the atom or the electron exactly, or a bond, period. Right? You have some distribution. Right? You've seen this before. This is what the orbitals and the atoms are. Right? The electrons don't orbit like a moon around a planet. They have these distributions, these orbitals, the P-shaped ones and the D ones and stuff. It's the same process, same idea. They have an average position, kind of tells you where they are roughly, but they can be anywhere. And there's an uncertainty to that because they can be anywhere within reason. Right? So there's always this intrinsic uncertainty. All right, so what happens when I go to really, really high n? So let's go to n equals 100. Right, n equals 100 will have 99 nodes. right? So it's going to be a really, really fast oscillating function, right? It's going to be a sine wave that oscillates very, very quickly. So I'm just going to roughly sketch it. Again, it's kind of hard to draw a 99 nodes in a small space, but the idea is that it's got to be all positive, sorry. The idea is that the wave function, or the psi squared, oscillates rapidly along the space of your box from 0 to L. Right? And imagine now we do it to n equals 1,000, which has 999 nodes. Right? And basically at this scale, right, at the scale of this drawing, what does that look like? Well, I'll tell you, it just basically looks like a straight line with a bunch of jagged BS in the middle, like this. But basically, the intensity distribution of the wave is blurred over because you're oscillating so quickly that on this scale, it doesn't look like a sine wave that's moving up and down and up and down. It's just going like this. Right? So it's up just as much, it's at the positive value just as much as it's at the negative value on average. And you basically can't tell where it's 0 because the places where it's at a maximum are so closely spaced together that basically it looks like a straight line. Right? So let's ask the question here. In either case, let's do the n equals 1,000 case because I think that's the most obvious. What's the average position of the electron? Well, it's still L over 2. Right? Because the potential is symmetric about L over 2. So it hasn't changed. But what's the uncertainty of our measurement? Well, the probability distribution is flat. It's uniform across the entire box. It's flat. It doesn't go up and down. So what that means is that there's an equal probability of the electron being anywhere in this box. Probability is effectively flat at this scale. So sigma x is basically the length of the box, or half the length of the box. It's L over 2 as well. Right? Or something on the order of L over 2. Maybe I'll write instead of equal sign that it's approaching L over 2. So what are the consequences of this? Well, the consequences are, again, the average is the same. It means that it's in the middle of the box. But now you have an equal probability effectively of finding it anywhere. There are no nodes, at least to your scale. It's just this constant probability everywhere. Right? So let's ask the question now. For a classical gas particle, all right, so just go back to last semester. We have an ideal gas. All right, we're just going to take one particle out of that gas, and we're going to ask, what's delta x, and what's sigma x for a classical particle? Well, remember, ideal gas, those particles move randomly and they fill the space. And the probability of them being anywhere in the box is uniform. Right? For a gas particle, they have an equal density at the edges as you do in the middle. It's all uniformly distributed. So there's an equal probability of finding a gas particle anywhere. But you can measure an average. If it's moving randomly, it's going to be on average in the middle of the box. And if there's an equal probability of finding it anywhere, the standard deviation is L over 2. So what happens? Well, as n increases, we've gone from, so if n equals 1, right, our previous situation, we've gone from a situation where, our electron's in the middle on average, but there are a discrete set of places where it can be. Right? It prefers to be in the center and not on the edges. But as you increase the energy, which is increase n, to higher and higher levels, we get behavior that looks more classical. And in fact, you can prove this. That as n goes to infinity, as the energy gets macroscopically large, when you get to energies on the order of a kilojoule per mole, chemical energies, physical energies of a gas at room temperature, your distribution probability, your wave function just looks like a classical particle distribution. Everything works exactly the same. And so there's a really, really big conclusion that you can make from this, and this is true for pretty much all systems, is that classical behavior, right, the ideal gas law, whatever you want to think of, emerges smoothly as n goes to infinity, as n becomes large. Okay? So the idea is that a classical electron, or let's say instead of electron, let's think of helium atoms or hydrogen, which is a very generic atom that's sitting in the box. That the gas particle becomes classical in the sense that it can be anywhere and it's all uniform and everything is like what you expect it to be. It happens when the quantum number is very, very large. Very, very large. Or another way to write it, for those who took thermodynamics with me, is that the energy of the particle, the difference between two energy levels, right? So the spacing between the energy levels is much, much smaller than the thermal energy available in the system. All right, so if you're on the order of 300 Kelvin, you've got 300 Kelvin worth of thermal energy in your system, like a gas, and you're at an N, your electron's at an N where the gap between the energy levels is super small compared to the amount of available energy, the system acts classically. All right, so what does that mean? Well, N equals infinity means you're at high macroscopic amounts of energy, and having a spacing smaller than RT means that effectively you lose your quantization. That the lines are so closely spaced together, you can assume that they're all smeared out and you have a continuum of energy levels that do exist in. All right, and this is called the correspondence principle. And this is really important because when physicists and chemists were developing quantum mechanics, they weren't sure, right? They wanted to have a theory that's unified with what they know, right? There's got to be some way to take quantum mechanics and reproduce what we already knew. Right? Everything has to be consistent. And that's exactly what happens. When you take it to the point where your energy levels are so closely spaced together that you can't tell them apart anymore in your system, which is like what a classical particle is. A classical particle can exist at any energy, right? It's basically the spacing between its energy levels are basically zero. So when you're in that limit and you have a lot of energy, you just get a classical particle back and it acts exactly the way you want it to. Right? That's what proved people that this is a consistent theory, is that you can get all of classical physics back by making this assumption. Right? By taking the energy really high and making sure that you have enough energy in your system that the spacings between levels is minuscule. So that it's easy for an electron to go from one level to another. There's plenty of energy to do that. All right, we'll see that the homework explores this. So I won't go too much into detail because the homework will explore this. The whole point of the problem to explore is to take this idea for the particle in the box and show that the correspondence principle works for the particle in the box. So you'll explore this in more detail on the problem set. What I want to do now with this information is I'm talking about a bunch of different things that we've measured. Right? I haven't told you how do we measure the average and how do we measure the standard deviation of something. Right? So I haven't come up with the formula to do that yet. I've just kind of intuitively told you that you have a width and an average here because you have a probability distribution. Right? This is like a bell curve of grades, if you will. It's the exact same concept. There's always going to be a standard deviation and an average. But how do you calculate these things for a wave function or for a system? And that allows us to start the next postulate, and perhaps the most important one. Well, it depends on who you ask. But for an experimentalist, it's certainly the most important one. If I can find my notes. Aha, here they are. Okay, postulate 4. All right, this is what's called the average observable postulate. All right, I'm going to teach you how to average, how to take statistics on our system. All right, and it's a super easy formula. All right, we'll work out a little problem. We'll work out some problems and look at this more carefully. All right. So I need to do a little writing. Let's set up this postulate a bit. So let's say we have a system. If a system is in a state described by a wave function, a normalized wave function, right? Remember, a normalized means it integrates, the square of it integrates to 1. I'll often simplify wave function at wave fn. I just get lazy. And occasionally I'm going to draw my wave functions with these little bars over it. That's a psi. It's a capital psi. I'll talk about what I mean by that next class. Why? What's the difference between a little psi and a big psi? But for now, they're the same thing. All right, so we have a normalized wave function psi. And we should also say that that satisfies our eigenvalue equation for an operator. Right, so it should satisfy any arbitrary operator applied to it gives you a number, O sub n times psi. All right, so it's a proper state for this measurable we're doing. So in this case, it's energy. Right, for the particle in the box, O here is h, and psi is our particle in the box wave function. Right. So what I want to do now is I want to calculate the average value that I get for O. The average, or the mean value, so the average value of the observable corresponding to O can be calculated as follows. All right. So when I write the average of something, I want to take the average of an operator. I write them in these angle brackets. Right? This is something from statistics and statistical physics, this notation. Right, so anytime you see these brackets, I mean average. Average of a variable. It's going to be equal to the integral over the space of the system. Right, that'll be our box. In the case of the box, I always just write space here. Each problem will have a different bound, but for our box, it's between 0 and L. Of the wave function complex conjugate, or I'll mention that one more time, times the operator evaluated on the wave function. And then times whatever our space variable is here. Okay. So what I've done here is actually seems kind of odd, but it's pretty straightforward. Remember that our normalization condition was that we took the integral of the square of the wave function, which is psi times psi, or psi star psi, if it's a complex function, and it equals 1. All right, so what I'm going to do to measure the observable is I'm going to jam my operator in the middle of them. So I have psi star O psi. It says psi star psi. So I'm going to jam this operator in the middle and evaluate it on the function to the right. So this operator is evaluated on here. I take this evaluation, right? Look in the case here. It's going to give me a number times the original wave function in this case. So I know eventually I'm going to factor a number out. And I'll get psi star psi. Okay, but that doesn't always work. All right, so but this is the general formula. And we're going to operate on our wave function, then multiply the result, which is going to be proportional to the wave function. Right? This operation gives me the wave function back, and then I'm going to integrate over the wave function squared, effectively. And this will give me the average of the value. Do this every single time, and it gives me the right result. If I know the wave function, I know the form of my operator, I can calculate an average. Right? This is what we do in experiment. Right? What I'm doing in my position box when I measure the position of the electron is I'm measuring the position of the electron 100 times, and then when I take an average, this is the equivalent. I'm integrating over the space of the wave function squared times the operator. So this is the mathematical form. This is very abstract. So let's do a problem. Let's do an example and see how this works. And again, it just comes down to a little bit of calculus. In the end, you're taking an integral. So let's do an example for our particle in a box. I want to write one more thing. For real wave functions, psi star is equal to psi. I probably wrote this before, but if your function's real, like our particle in a box wave function doesn't have an I, then the complex conjugate's the same as the wave function. So you can always simplify them. All right, and most of the time we're going to be doing things in real space anyway. So this is almost always true in this class. All right, but I need to be precise because it'll be helpful later on. Because again, not everything is real. Okay, so let's do an example. Let's just show, again, remember that I said for the particle in the box, regardless of the value of n, the average value of x for the particle in the box is L over 2 for the PITB, particle in the box, or the pain in the butt, whichever one you want to think about. I know Abby up here probably thinks it's a pain in the butt. So how are we going to calculate this? Well, we just apply our formula. Let me actually make a little more space here for myself because I got to do a couple steps. Let me just draw a nice line here so we don't have to worry about it. Okay, there we go. Okay, so the average value of x is going to be the integral over the space of the box, which is 0 to L, of our wave function. We'll just write any n for now. Right? There's a factor of 2 over L sine n pi x over L. So that's my psi square. That's my psi star. Remember, it's the same as the wave function because it's real. Then I have my operator O, but in this case that's x, and the operator for x, if you go back to our table from a couple weeks ago, is just x. We put an x here. That's our operator times our wave function again. And this is over x. Okay? So in order to calculate this average position, I need to take an integral of some sines and an x. All right, so let's simplify this out and see what we need to evaluate. Right? Again, these are just algebraic equations. So because x is just an algebraic variable, I can move it anywhere I want. Now you can imagine if the operator was a derivative. So if this instead of x was d by dx, I'd have to take the derivative of the thing on the right first before I do anything. All right, we'll look at that in a second. But in this case, it's just x. So we can move it around a little bit. I'm going to factor out the 2 over L, right? We have two factors of square root of 2 over L, so that gives me 2 over L. Integral from 0 to L of x. And we have two factors of sine, so it's x sine squared n pi x over L dx. Okay? You can put this into, I did it for the other class, I'm not going to do it because it's just a waste of time. You can literally put this into Wolfram alpha and it'll evaluate it perfectly for you. Okay? There's also a nice table on Canvas under module 0 of common integrals. And I'm pretty sure this integral is in there. Anyway, it's very easy to find. If you type in common integrals for quantum mechanics on Google, you'll find tons of resources. Right? Pretty much no integral in this class you'll have to do on your own. Like you'll be able to massage it into a form and then evaluate that form from a table or from Wolfram alpha. All right, things are very straightforward because these things have been studied to death and this is not a math class. And Einstein always told us that real scientists look up data when they don't understand something, they don't memorize it. They learn how to look it up. So I'll leave that to you guys. But anyway, you can solve this very easily by doing a U substitution here on the interior here, and then integrate by parts. All right, so it's kind of a pain in the butt, but it just uses Calc 2 knowledge, integration by parts. And I'll give you the result. Right, and I got this just from, I did it by hand, but I'll just tell you what Wolfram Alpha gives you effectively in steps. All right, I just need to find my result here. So the result of this, again, we get the factor of 2 over L on the outside, and the result of our integral is L squared over 4. All right, so once you integrate this out, you get L squared over 4. Right, and it should be obvious to see here you get L over 2, right? We cancel out the 2. Let me do a different color. Cancel out the 2, cancel out the square, and this becomes a 2. This goes away, and we're left with L over 2. Simple as that. Okay? You're going to see this sign squared all the time. Right? Anytime we're going to calculate something about the particle in the box, you're going to always have 2 factors of a sine or a cosine, depending if you take a derivative or not. It's either the derivative of sine cosine. So if your operator is a derivative, you'll get a cosine. Right? So most of the integrals and pretty much all the integrals in particle in a box are functions of sines and cosines and x's. Right? It's all trig. Right? So it's very, very similar. Everything kind of looks the same. Right? So let's look at a slightly more complicated example. And this integral you can do with some evaluation. You don't have to write any math out. All right, so let's look at the integral. Let's just do for fun, right? Well, that's the position. What's the average value of the momentum? All right, remember momentum is it's a vector. That's the first important point. So it's a mass times velocity, right? Velocity has a direction. Okay, so there's some directional information in here that we're kind of averaging over, right? Because velocity has an x direction. It can go backwards or forward. So there's a direction as well. But we'll have to see what happens with that. We always have to keep that in mind. And remember that the operator for momentum, I'll just put it over here, piece of x, is minus IH bar d by dx. Right, it's the first derivative. Okay. So how do we do this? Well, it's the same formula. We're going to take an integral from 0 over L of psi times p hat evaluated on psi dx. And that's going to be, I'm going to factor out the 2 over L's because we're going to have 2 signs in here. That's going to be sine n pi x over L. This is integrated from 0 to L. Times minus IH bar times the derivative of psi with respect to x dx. All right. And remember, psi here is, well, I'm going to get rid of the 2 over L, but just the function part of it, approximately equals sine n pi x over L. So what's the derivative of sine? Well, it's cosine. So it's going to be n pi over L cosine n pi x over L, right? Just doing the chain rule. Okay, so now we have it. I'm going to factor out the minus IH bar. So we have minus 2 IH bar over L. Should be scary that we have an I in here. But let's see what happens. We have an imaginary momentum. That's strange. But let's make sure everything works out before we worry about that. We have the n pi x over L. That's our psi star. And then our derivative times our derivative, which is just cosine. All right, we have some numbers to factor out with the n pi over L. So this is minus 2I n. Sorry, let me do it differently. Let me get the n on the end. 2I pi n over L squared times the integral of 0 to L of sine n pi x over L cosine n pi x over L dx. Okay, so now our integral, because we took that derivative, that sine that's usually on the right has become a cosine. And so our integral is now a sine of some argument times the cosine of that argument. But before we evaluate this integral, right, we can do trig integral, use substitution, all that junk. We don't have to do it for this. And let me show you why. Let's just plot these two functions, cosine and sine. Let's just pick an n. So let's do it for n equals 1. It's true for all of them. But n equals 1, it's the easiest to see. So for n equals 1, oops, sorry. Our wave function, our sine, looks like this, right? And what does the cosine squared, what does cosine look like in this region? Well, cosine of 0 is 1. And it decreases until L over 2 and comes back up like this. All right, so this is our cosine, and this is our sine. Right, and our integral is going to be the integral of the product of these two. So let's look at what the product of these two looks like. Draw another coordinate diagram. A really small one there. I'll do it in green. So let's just kind of look at the general behavior. At 0, we have a positive number times 0, so the product of sine times cosine is 0. I need a little more space. I'm sorry, guys. I need negative here. I just need to have a negative axis. Just a little bit more space. I apologize. I'll put it here. There we go. Okay. So now we're going to do sine cosine. So this is sine. I'm just going to type sine cosine. It's the product of them. That's what we're integrating. So at x equals 0, it's 0. At x equals L, it's 0. And then there's going to be two maxima right here where they intersect in here, and then there's going to be a minimum here because you have a negative sign here. Right? These multiplied together is positive. They're both positive here, but negative here. So this product is going to look something like this. And what you can show, just a little bit of math, right? Our integral is going to be the integral of this region in green minus the region here in purple. If I cut this function in half, this positive region right here, is the same width as this negative region on the left side of this. This negative region on the right side of this white line is the same area as this one right here. So we have a plus a negative value of the same size, that's 0, and we have the same thing over here. This whole integral is 0. And this is true for all n. Right? It's harder to see for the higher frequencies, but they cancel each other out. The integral cancels out. So what does this mean? This means that the average momentum of our electron is 0. So what does this mean? Does that mean it's not moving at all? No, not at all. Remember, momentum is a sign quantity. It's a velocity, so it has a positive component or a negative component. So P has some averaging over this position, or this direction. Right? You're averaging over the direction. And in fact, the matter is the electron has equal probability to go backwards as it does forwards. So its momentum in the positive, its momentum probability to be positive is the same as it to be negative. So the average is 0. So this doesn't mean the electron's not moving. It just means that it's equally likely to move to the left or the right. This means that P to the left is equal to P to the right. Right? Equally likely to move negative x as plus x. Right? It can go forward or backwards equally likely. All right, so this tells us it's not. It doesn't tell us it's not moving. It can be moving in either direction. So it doesn't really tell us a lot. So the question is what can we learn about the momentum, the actual motion of our electron? Well, if P just tells us 0, that just means it's equally likely to go positive or negative. Like the vector can be in this direction or this direction. What's the thing that's conserved in both situations that doesn't change? Well, the length of that vector, the magnitude of the momentum. Right? So the magnitude of the momentum is P squared. Right? This is the magnitude of that velocity vector times mass. Right? And what's that going to be? Well, the integral from 0 to L times 2 over L times sine n pi x over L times minus I h bar d by dx psi squared dx. Oh, sorry, not the square's on the, sorry, the square's not on the wave function on this one. It's being operated on. Right, and this is the same as, I'm just going to factor a few things out. 2 over L, we get the minus sign, let's square the minus I h bar, minus times minus gives me 1, I squared gives me minus 1, so we get a minus sign here, h bar squared, integral from 0 to L of sine squared n pi x over L dx. Okay, I won't calculate this, but you're integrating, right? If we think about that multiplication thing we did with sine and cosine, it cancels out. Let's do the same thing here. We're multiplying a sine by a sine. They have the same phase, the same symmetries and everything, so they won't cancel each other out. So this number is positive. It's positive. Greater than 0. So what does this mean? Well, it means, and it has to be positive, right? Because, why does it have to be positive? We can just argue this. Well, because the kinetic energy of the particle, which is not equal to 0, is equal to p squared over 2m. Right? So that means that energy, the average value of the energy, is proportional to 2m times the average value. Sorry, that's the wrong, sorry. 2m times the average value of energy is proportional to is equal to p squared. So if we're at n equals 1, right, we're in the ground state, we have some energy, right? So that means we have some p squared. That means the particle's moving. It's always moving. Right? E is always greater than 0 for the particle in the box. So particle always is moving in some direction. Okay? Right? And it's really easy to calculate the value of this. You don't have to do an integral. You can if you want. Right? You know what E is for n equals 1. It's h squared over 2ml squared. So you can plug it into here and you get the value of it. Right? You can relate energy and p squared. Right, so energy tells us something about, right, so energy doesn't tell us about the momentum of the particle, but it tells us about the magnitude of the momentum of the particle. So it doesn't tell us anything about the direction it's moving, because in this situation it can move either direction. It's zero. What energy tells us is about the magnitude of that vector, the magnitude of the velocity, the speed, if you will, of the particle. And the speed has to be positive. It's always moving, always constantly moving, and you can calculate exactly how fast it's moving. You calculate the momentum squared, take the square root, and divide by the mass, you get the velocity, the average velocity of the system. Right? And you'll see the electron is always moving in the box, constantly moving. It just doesn't matter whether it's moving to the left or to the right. We're going to find systems where this does not happen. All right. In fact, when I don't want to talk about it too long. When we get to the hydrogen atom, when Niels Bohr starts to come up with a model for these orbits for the electrons, he predicts that the electron will always have angular momentum. It's always orbiting at some velocity around the atom, no matter what the state is, just like the particle in the box. Right? The particle in the box is always moving. So he thought, well, that must mean in an orbit, the electron's always moving too, with some angular momentum. And that's true for the Earth and the Moon. If the Moon didn't move, if the Moon didn't orbit, didn't have angular momentum, it's just going to sink right into the Earth. Right? The only reason why it keeps its distance is because it's orbiting, it has angular momentum. Right? So only all stable orbits have angular momentum, but not in quantum mechanics. We're going to find that in the electron, there are states where the electron is not moving. It has no angular momentum. Very, very interesting result. All right, so this isn't always true, but it is for a particle in the box. I have one more thing I want to mention, one more tool that's helpful for the problem set, and then we'll talk a little bit more about it on Tuesday. Again, the last thing we want to calculate that we've talked about is the standard deviation. So I've done averages. How do we do standard deviations? Okay. So it turns out you can relate the standard deviation of a measurement or a variable with its averages. So the standard deviation squared of a variable, let's say x, this is called the variance, the square, is equal to the average value of the variable squared. So you're going to take the average of x squared minus the square of the average of the variable. All right, so this is called the second moment in statistics, and this is the first moment. And so that means, therefore, the standard deviation is equal to the square root of this. The textbook doesn't, I think it uses this notation, but it sometimes also calls this delta x. Or delta or sigma, depends on who you ask. All right, so again, all you have to do is just do these little averages. Okay, so for the, just I'll write it down, but you'll do this on the problem set. Sigma x, I'm just going to write squared so we don't have to take a square root, is going to be equal to the average of x squared. That's going to be the integral from 0 to L of psi n of x times x squared times psi n of x dx. Right, this is my x squared average. Minus the integral from 0 to L of psi n of x times psi n of x, which we calculated already for a particle in a box. Right, so it's the difference of these taken to the square root. We're going to, we have to square this, of course. Right, you have to square on the outside there. Highlight that. And then highlight this, right? That's the difference between these two. And of course, this is going to be equal to something. I'll have you evaluate this in homework. And you know what the other one is? It's L over 2. We calculated it. So this is minus L squared over 4. Right? And we showed kind of what we kind of showed graphically is that as n increases, sigma x is getting bigger and bigger and bigger. And you'll see that this, right? So this part right here doesn't depend on n, right? It's fixed everywhere. The average is fixed for all n. But the second moment is actually dependent on n. And you'll see that this scales with n. Okay? So as n increases, this term gets bigger and bigger and bigger. The second moment gets bigger because the electron tends to be further and further away from the average. The middle of the box as n gets bigger. That's what we saw. So this number gets bigger as n gets bigger. The average stays constant. And so the whole thing scales with a function. I think it's a function of n squared or n. I forget exactly. I think it's n squared. So what that means is that the standard deviation, the uncertainty of your measurement of where the electron is, gets bigger as n increases, which is what you want. Because at the classical limit, which is n infinity, or n huge, very large, is that you don't know where it is in the box. It can be anywhere in the box. Right? That's what an ideal gas is. It can be anywhere in the box. So this should get bigger with n, and it does. Right? So the homework will have you calculate this. Okay, that's all I have for you today. So have a lovely weekend. I will upload this and the lecture today when I get a chance. Office hours tomorrow morning, 11:30 to 1:30, and otherwise I'll see you guys on Tuesday. Have a good one.